Oops. Physics Olympiad. This is 2009, problem A3. And it's one of my favorite problems because usually the USAPHO, all the problems are challenging, but I especially like this one because it can be solved using some pretty elementary methods from like high school physics, maybe AP Physics C. But yeah, so the problem is okay, so we have two masses M. They're like it's a binary star system, and if you study some astrophysics, these are pretty cool. And they're rotating around their center of mass, and there's this little mass boy, and he's like little m, and he's distance, I guess, what is this, like z. Yeah, hopefully you can see that. And so basically the idea is like these masses are rotating around each other. Well, this is going the same direction the whole time. And while they're rotating, this mass is oscillating up and down like that. And so if if these masses rotate with a period of Ts, and this oscillates at a period of Tp, we want to find the ratio of Ts over Tp. And we know that m is much smaller than m. And this entire distance we'll call it d. So this is d. And so one of the most, I think, beautiful things in physics is the idea of simple harmonic motion. And what most high school physics teachers won't tell you is that whenever you have a differential equation, and probably because in high school you don't learn differential equations, but whenever you have a differential equation of the form x double dot, that's the second time derivative of x, equals negative something x, and this something could be anything, then you have this is an equation for simple harmonic motion, and you get that omega, your angular frequency, is the square root of something, and your period is 2 pi over omega. So it's 2 pi times the square root, and I'm running off the page, 1 over something. Okay, so, why is this true? Well, if you try to solve this differential equation, like omega, it's solved by x equals e to the I omega t, right? If you take the first derivative with respect to t, you get I omega e to the I omega t. And if you take the second derivative, you get I squared is negative 1, so you get negative omega squared e I to omega t, which is negative omega squared x. And so that's why it's called omega, because usually you call these solutions e to I omega t, and that's why it's the square root of something. Okay, so now let's solve the problem. I guess one more thing I can add is that's why, if you have like a thing on a spring, a block, that it has a restoring force. So a restoring force is negative. There's a restoring force, F equals negative kx. And we also know that F is ma, thanks to Newton, but we can write the acceleration as x double dot, the second time derivative. So then you get x double dot equals negative k over mx, and this is your something. And so omega, and this is the more familiar omega, is root k over m, and t is 2 pi root m over k. And you can also do it for the pendulum. I don't have time in the video because I actually want to get to this awesome problem. So let's see if we can rush through it real quick. Okay, so the first thing we should try to do is find Ts, the period of the big masses. So we know they feel a gravitational force between them. G, M, M, over d squared, the distance between them, the two masses. So F equals GMM, which is GM squared over d squared. And now, since they're rotating in a circle, we also know there's going to be some centripetal force pointing like this. And so the gravity is responsible for that force. So at the same time, we know that this is mv squared over r. Well, r is d over 2, so let's just say d over 2 equals r. So mv squared over r. And what is v? So how fast are these guys going? Well, v is the total distance over the time, or the period. So it should be 2 pi r, well, v squared is 2 pi r over t squared, which is 4 pi squared r squared over t squared. Great. So now if we set these equal to each other, we can solve for t. This is our ts. So we have gm squared over d squared equals m 4 pi squared r squared over ts squared r. So we have to move some stuff around. Let's see if I could do this right. T squared goes on the other side, and we move everything else over. So we should get 4 pi squared r d squared over gm. And r is d over 2, so this is 2 pi squared d cubed over gm. And so we get ts equals pi times the square root of 2d cubed over gm. But, you know, we saw, like, our periods were in the form, like, 2 pi times square root of something. So, to make this of the same form, we can multiply inside this by 2 over 2, and then pull out the 4, and we get 2 pi d cubed over 2 gm. So that's our ts. And so, what about TP? So this, oh no, where's my paper? This is the period of the little guy going back and forth. And one thing to notice is, so the force he feels a gravitational force from each of these. They're pulling him towards him, right? And this distance, if this is r, and that's z, and this is square root of r squared plus z squared by the Pythagorean theorem. But what you notice is, since these masses are equal and they're the same distance apart, the x component, they just cancel out, right? They both pull like this way, and it cancels out. So they're both pulled down with some force. And that's actually going to be the restoring force, because it wants to be here, and the gravitational force restores it to here, and when it's over here, it wants to go back to this sort of equilibrium point. So the force, alright, the force equals, it's a restoring force, so it's negative 2, because there's two masses pulling on it, 2 gm, this is the force due to gravity, little m, over r squared. Well, what's the r? R is this square root of r squared plus z squared squared. So that's r squared plus z squared. But we want the y component of this force, right? Because right now this, let's see, how can I do this? Okay, I can't, okay, let's do like that. Right now, this force is the force along this whole direction, but we just want the y component of that. So if you imagine this was like some angle theta, we want like this force times sine theta. But sine theta is opposite over hypotenuse. Opposite over hypotenuse. So this is negative 2gmm over r squared plus z squared times z over, that's the opposite, over the hypotenuse, which is r squared plus z squared. Now, okay, so let me just write this fully. This is negative 2gmm over r squared plus z squared to 3/2 z. But we also know that the force is mz double dot, or the acceleration in the z direction, which is negative 2gmm over r squared plus z squared to 3/2 z. And if we cancel out of m, we get that this is z double dot equals negative 2gm over r squared plus z squared to 3/2 z. Now this looks exactly like what we wanted, right? Like some second time derivative equals negative something, the same thing, right? That's exactly what we have. But there's one thing we want to do to make this nicer, is we realize that, okay, like this mass is tiny and it's oscillating. This z is probably going to be tiny compared to the very large distances these stars are going to be rotating away. So we can say if r is much greater than z, then we have z double dot equals negative 2gm over r cubed z. Right, because z is just so small in comparison, it kind of just goes away, and we only have to, the r is kind of going to dominate this term right here. Great, so we're almost done, because now we know how to solve this. This gives omega equals root 2gm over r cubed, and so the period Tp is 2 pi root r cubed over 2gm. Okay, and now we want to put it in terms of, so I guess we could put this one here back in terms of r. So this is 2 pi, let's see, d equals 2r. So this is root 4r cubed over gm. We want the ratio ts over tp. So finally, ts over tp equals 2 pi, hopefully I did this right, 4r cubed over gm divided by 2 pi r cubed over 2gm, which is, let's see, did I do this right? D is 2r, so you get 8r cubed. Yep, okay, and then this is 2gm, yep, r cubed over 2gm, yep, that looks right. So then, what is this ratio? This is just going to be 1 over 2 root 2. Yeah, and so you might notice that if you look up the official solution online, it gives a solution of 1/2, but 1/2 is incorrect. This is actually the correct solution. So hopefully you enjoyed